Hello, my name is Fernando Arreola. This is Brian Crane and Elisa Rodriguez. We're from the University of Arkansas, Williams College, and Ursinus College, respectively. And today we're going to be talking about the Diophantine equation, ax squared minus b to the 2m is equal to plus or minus y to the n. But first, some history. The field is named after Diophantus of Alexandria, who lived around 200 AD in Alexandria, Egypt, after his work was rediscovered in Western Europe after the Dark Ages. His major work consists of 13 books, and some of which are now lost, which came to be known as Arithmetica. These books contain a collection of problems with numerical solutions. The problems found in Arithmetica can be formulated into what we now call Diophantine equations. But let's define what exactly a Diophantine equation is. More than likely, you are already familiar with these equations. A Diophantine equation is simply a polynomial equation, usually with two or more unknowns with integer powers and coefficients, though you'll see rational coefficients as well. So let's take a look at some examples. These are examples of Diophantine equations, many of which have nice geometric perspectives or a long history behind them. The first equation that you see here is the famous Pythagorean theorem, which, as we know, states that the sum of the squares of a triangle's legs is equal to the square of its hypotenuse. And if you recall from what a Diophantine equation is, we are only interested in integer solutions. Hence, the equation here defines Pythagorean triplets. Next up, we have the generalization of the Pythagorean theorem, Fermat's last theorem, which went unsolved for centuries until it was solved in 1994 by Andrew Wiles. And lastly, we have Pell's equation, which is represented by a hyperbola and whose cases have been studied since ancient times in Greece and India.
So specifically this summer, we focused on a different Diophantine equation, specifically ax squared minus p to the 2m equals plus or minus y to the n. We determined that there are only finitely many integer solutions to this equation. We are able to do this with some key restrictions. So we're going to note that a is square free because it is sufficient to only look at those cases. If a was not square free, we would be able to pull the square portion into the x squared part, and then we'd be duplicating cases. We're also going to note that p is odd, p is an odd prime, and y is also odd. This is just because p equal to 2 is a special case that has different methods, and that when y is even, there's a possibility that we'd have infinitely many solutions. But wait, there's more. We were also able to develop a bound for these solutions. We have an upper bound on this n. So the question is, how are we able to do this? So we used a variety of methods, specifically p-adic valuation. So first, we're going to go over some definitions to help us understand what p-adic valuation is. We're going to look over some propositions and then see how that helped us determine some bounds that are very important. Then we're going to go into linear forms and logarithms, kind of the second part of our research. We're going to go over what that is specifically, how we were able to use propositions and theorems relating with that, and to get another bound that helps us with our research. All right, so what is p-adic valuation? So we're going to start with the definition, and we're going to start with a rational number x, and we're just going to define that to be a over b times some prime number p raised to an exponent r. So we're just going to note here that a and b are co-primed, and they're also co-primed to p, so a, b, and p only share the common divisor of 1. So we say that the p-adic valuation of a rational number x is just that power r. So whatever our prime p is being raised to, that's what the p-adic valuation is of the number. So to better understand this, let's just go over a few examples. So the first example we have here, we're looking at the 3-adic valuation of 6. So we know that 6 is equal to 3 times 2. We have 3 raised to the first power, so we're just going to say that it is equal to 1, the 3-adic valuation. So now that we're looking at some more examples, let's get into something a little bit more complicated. So we have the 7-adic valuation of 1/4 times 7 to the 5th. So again, based on our definition here, we know that it is our value r. So we're looking at what this power 7 is raised to. So what do you guys think it is? You can put it in the chat, say it out loud. Okay, I'm getting some good answers. Okay, you guys are right. So it is equal to 5. Awesome, awesome. So now let's go on to a more complicated example. So we're now going to look at the 5 adic valuation of -3/25. So what do we have any ideas here of what this could be? Let's break it down. So if we were to go ahead, we're going to see that really this is equal to -3/1. So just kind of putting it in that format that we're familiar to, times 25 to the -1st. So we're able then to take that 5 adic valuation, looking at our prime p is 5. We know that 5 squared is equal to 25. So we just put that negative in there. So those are some examples so that way we can better understand it. So now that we've kind of done this, let's look about how does this actually help us. So we're able to use some bounds for these types of things. And this is really important because p-adic valuation is heavily studied. It's a very interesting area of math, and we're actually able to get some bounds on p-adic valuation. So specifically, this theorem from Yu in 2007 gives a great upper bound on the p-adic valuation of a product of algebraic numbers raised to these integer coefficients -1. So basically at the top here, we just have this kind of thing. And we're going to let this p-adic valuation just be denoted by this alpha sub m. And although this looks really intimidating, there's a lot of things going on. The main idea here is that we're able just to get this upper bound. We're saying that we have some p-adic valuation and we're able to bound it. And a lot of these pieces are actually computable pieces. We're able just to say that most of these things are constants, and these parts over here, looking at this definition here, we're able to define them. So although it looks really intimidating, it's really easy to get these upper bounds. And we end up getting an upper bound on the p-adic valuation, which is awesome. And this is actually helpful for us. So specifically in our case, when we apply Yu's theorem, we're able to get an upper bound on m, since our p-adic valuation that we're dealing with is m. So we're able to get an upper bound with some of these computable constants and some logs. And although we wanted to get a bound on m and we have it here, we still have just a really small problem. Right here, we have this log epsilon, and log epsilon's not exactly bounded at the moment. So how do we get around this? We're actually going to go forward into our second method that we use primarily, and that's linear forms and logarithms.
All right. So to introduce linear forms and logarithms, it's probably best to start off with a definition. What is a linear form in logarithms? It's usually denoted lambda, and it looks like what you see on screen right here. And it's these b sub I are all integers, alphas are algebraic numbers, and it's just a linear combination of logs of them. And so these objects are important because they're really well studied. Alan Baker was one of the first and most prominent mathematicians to study them, and found that there's an upper bound on the log of this linear form in logarithms. So you got two logs going on, and it's given by this minus c log b, where c is a computable constant, mostly based on the alphas, and b has to do with the lowercase b's, the exponents, if you will. And then it has been refined over the years. So Laurent Mignot and Nestorenko have found this bound. Note that it looks very similar, but expanded almost. So you can kind of see the C part, and then you have like this log A1, log A2, kind of looks like the log B, and they are very related. And note here also, every coefficient that, or every constant that you see is computable just by going through the paper. The exact definitions we won't go over right now though. And so in our paper, we apply it, we do some math, and we end up with something like this. And so this is a pretty good bound on n, but there might be one thing that you're noticing, is that we have a bound on n, and it's in terms of n. You can see this log n over here, as well as the n over here. And so what do we do about that? So I'll give you guys a moment to pause if you want to think about it. And we're back, and we can think about growth rates. So we know for sufficiently large n is going to grow way, way faster than log n. So it doesn't really matter what coefficient you have on there. At some number, this inequality will be false. So you can search for that number. The exact method of doing that we won't go over right now, but you can simplify the bound to just some constant. And so remember, as earlier, this log rho is the fundamental unit of the field A. So since it's reliant only upon A and P, we can say for any given A and P, there is a bound on N. And so what do we do with that? How do we show that there's finitely many solutions? Well, luckily, Katov wrote a paper in 1976 that outlines how you can, how we can use, and excuse me, sorry. And we can use this theorem to show that there are finitely many solutions. So take any integer n and look at this portion right here. So this ax squared plus by to the n. In our case, let's just say that b is 1. So we have ax squared plus y to the n is in here. This denotes the greatest prime factor. We already know that it's equal to p to the m. So this whole side is just equal to p. And we have that it's greater than or equal to some constant times log x times log x. And this capital X, as written up here, is the maximum of x and y. So this allows us to put a bound on x and y. And if you have a bound on x, y, n, p, a, it all kind of falls into place. You know that for any n, there's going to be finitely many solutions. And since you have a finite number of values of n, it's just finite times finite, and you're all set.
Unfortunately, we were unable to fully settle this Diophantine equation, since our methods do not work for the negative case of the equation with the prime power m being odd. If you recall, our equation has the prime power be even. A quick overview of how our method fails is as follows. Our equation can be factored in such a way that the left-hand side of the equation is equal to some epsilon times rho, where epsilon is a non-unit element of Q adjoint root D, and rho is its fundamental unit. After this factoring and some arithmetic, our method yields that negative y to the n is bounded above by root D. However, it is not known if D itself is bounded. Further, our factoring requires the equation that you see on screen to be a perfect square. However, through a computer search, we can find many counterexamples to this claim. But it gets worse. Assume this equation is not a perfect square. Then a similar issue as before arises, where the bound on n contains some root d. But d is not known to be bounded, so we're unable to say anything about a bound on n. And these are the current issues that we experience. And this is the end of our talk. And if you guys have any questions, please feel free to email us. We'll be happy to answer any questions that you have. Thank you.